Yeah, Harsh, thanks for reminding me. So for the sake of the recording, I'll just go back to this beginning of the discussion. What we're doing is we're starting today by understanding reflection of a transverse pulse from a boundary. So a single pulse traveling along a string. We had seen equations of single pulses before. For example, we had seen a pulse can be represented by an equation like this: exponential pulse, this type of pulse, or it can be a hyperbolic pulse traveling along the positive x direction with the speed of omega by k, that kind of pulse. Now, what is happening is that the string at the other end has a point which is attached to a rigid boundary or a rigid wall, such that that point now acts like a hard boundary or a rigid boundary because it cannot move. So we want to understand that how the reflection of this pulse will happen from that boundary point. That is where we are at right now. So now let us look at closely the situation as the pulse just about reaches that boundary wall. So as the pulse right now, let's say it's like this. So as of now, the shape of the pulse is intact. It is D and D and H. But notice what happens is that the point P cannot be displaced. Okay. The boundary point P, at the point P, the displacement along the y-axis is 0. So as a result of that, what happens is that next snapshot picture, when we look at the pulse having come a little closer, you'll see that the shape would have first changed like this, where initially the height remains the same, but the pulse becomes asymmetric. Now you can see that this distance has become, let's say, delta x, which is less than d. Then an instant later, what we'll see is that something like this happens. The pulse's height also diminishes. And then we'll see at a particular instant of time, the string would have become flat. And next instant, what we'll see is an inverted pulse appears. And eventually this inverted pulse increases in size. And eventually it becomes a perfect inverted image of the original pulse, assuming that there's no loss of energy during the reflection, which is a bit of an idealized situation, but so this is the process of reflection. And once this reflection is completed, the reflected pulse is inverted in phase. So this is the sequence of events that occur. If I draw a diagram to try and superimpose all these, you'll see that the original pulse let's say like this, then it transforms to this, then it transforms to this, transforms to this, then the string becomes flat, and then eventually you see that this happens. So we have the phase inverted reflected pulse. Okay, now it's very interesting to note what happens in terms of mechanical energy here. A single traveling pulse of this type is actually carrying both kinetic and potential energy with it as it travels. But as it reflects, what happens is at a certain instant, the ratio of kinetic and potential energy that it's carrying starts to change. And it reaches a situation where it has a lot of kinetic energy, but hardly any potential energy. And then again, that maximum kinetic energy is converted to a combination. And by the time the inversion is completed, it has that same kind of balance of kinetic and potential energy as the original incident pulse would have had. So this is our incident pulse in this diagram. And once the reflection is complete, this is our reflected pulse. Yes, Ramon, I will scroll up. Okay, so if this diagram set is clear to all of you, let me just scroll up for a moment. Okay, so there are two interesting things about this whole mechanism of the reflection of the pulse. One is, as I was telling you, the mechanical energy of a traveling pulse. We'll track that as it propagates, and also as it reflects. Let's understand both these things. Okay. So imagine I'm drawing somewhat of a magnified kind of diagram of that traveling pulse now. So what is happening is that at this point of time, if you understand this portion of the string and this portion of the string, they are under maximum stress, longitudinal stress. Because this is the part which is stretched out. Again, this part has minimum stress. And this here has zero stress. This here has zero stress. Now also, one more thing you'll understand is that as this pulse progresses, how the medium particles are moving. So let's understand that also. Okay, so this is the pulse at time t. Okay. Now, just a moment later, at time t plus dt, the pulse would have become like this. Okay, so you can see that as this pulse is propagating, these particles have maximum downward speed and these particles have maximum upward speed. So again, this region and this region has maximum kinetic energy for particles of the string. And the particles that are located right at the peak position at that instant, they have minimum kinetic energy because they've reached their maximum of displacement. So their particle velocity is tending to zero at that point. And again, this region has zero kinetic energy. Zero kinetic energy. So basically, looking at the whole pulse once more, it's along with it, it's carrying both a combination of kinetic and potential energy. So such a pulse as it is moving, it's carrying both potential energy as well as kinetic energy. So the energy propagates in this direction. Through these diagrams, you can understand that as I said, a pulse which is propagating carries with it a certain amount of fixed mechanical energy, which is why the shape of the pulse remains constant. If we are assuming it's not dissipating energy. Okay. So as a pulse propagates, it carries mechanical energy, elastic potential energy plus kinetic energy. Now let's understand what happens to this energy as it reflects of a rigid boundary. As it reflects of a rigid boundary, what happens to the energy? Okay, so now as the pulse reflects, let's try to understand how this energy redistributes itself. Okay. And instead of the propagation going in the forward direction, the propagation is in the backward direction. So you can see here that in this diagram there is a certain amount of kinetic energy carried by these parts, and there is a certain amount of elastic potential energy because this part is stretched. But now next what is happening is that the shape of the string is changing in such a way that it's not symmetric anymore. So in comparison, this has got a total energy which is a combination of potential plus kinetic energy. Yes, and shall go back to that. Okay. But next instant, it's got the same total energy, but it's got in comparison more kinetic energy because these parts are rapidly coming down. Where the kinetic energy is increased compared to the earlier kinetic energy. Potential energy is decreased because you can see the size of that shape has become less. Now the physical dimension has become less. Okay. So as you are going forward, okay, the pulse's shape as it is changing from this to this to this to this. So as the shape is changing to a diminished size, the elastic potential energy is decreasing, but kinetic energy is increasing. And all that is happening because of the forces, elastic forces that are acting near the rigid boundary. So finally, when it reaches this position here, where the string is flat for an instant, it has zero potential energy, but these particles are on their way down at a very high velocity. Okay. So it has maximum kinetic energy and zero potential energy for an instant. And now next, the shape is progressing such that its size is increasing now. So again, kinetic energy starts decreasing and potential energy starts increasing as the size increases. And eventually, same potential energy and kinetic energy combination as it had before. So this is just for you to understand so that conceptual questions based on this MCQ conceptual questions you can answer. Like, when the string is exactly at that position where it has become flat for an instant. Okay. What can we say about the mechanical energy of the pulse? It is purely there in the terms of kinetic energy. It's not that the mechanical energy has disappeared and suddenly it will come again. Okay, so the particles of the string, they have reached that all of them are at the mean position simultaneously. So you're not seeing any pulse for an instant, but they are having a very high downward velocity because next instant you're going to see a pulse created with an inverted phase. So all the mechanical energy, which was the combination of kinetic and potential energy, is changing in the ratio of that combination as the pulse is coming closer and closer to the boundary. So it is diminishing in size. So potential is getting converted into kinetic. And for just a split second or for an instant, it is pure kinetic energy. And then again, it starts inverting in kinetic energy conversion to potential energy. And eventually it achieves the same balance of kinetic and potential energy as before. Okay. So this is about reflection at a rigid boundary. So I'll request of the students, I'll just give a bit of time to go through this earlier section and then this section. Okay, very good. Okay, now another useful way to understand the shape of the pulse as it reflects is you can understand the reflection of a pulse at a rigid boundary in comparison with another situation with a superposition of two opposite phase pulses traveling in the opposite directions. If we compare these two situations, it gives us a very nice way to understand the shape of the pulse as it progresses. For example, here we have this pulse going like this. Now, on this side, we will consider a situation like this, where we have two pulses which are otherwise identical, but they are traveling in the opposite direction. And so, as this pulse comes here, the situation is something like this now. Okay, now the interesting thing really starts happening, that we'll see that as these pulses traveling in opposite directions overlap with each other, how it changes the shape of the resultant wave, the resultant shape of the string, how it changes in this case, and correspondingly how we can see it will change over there. So here what will happen is that as these overlap, suppose this pulse on its own would have been like this after a little bit of time, and the other pulse on its own would have been like this. The resultant superposition now will lead to something more interesting. I'll draw this a little better. This is what this will look like. So correspondingly, see what this looks like. Then after this, there is an instant when the two are almost fully overlapped, or they more effectively overlap. Let's say one pulse is here, other pulse is here. So their superposition is resulting in this kind of a thing. So over here, and then we have a situation where the two pulses are perfectly overlapped. There they have a cancellation kind of effect. So effectively, the string is at rest for a moment. I mean, at the mean position for it. That's what happens. And then next moment, the inverted pulse has come to the left hand side. Whereas so their superposition will now look like this. and then eventually you have. Okay, so you can see the comparison of reflection at a rigid boundary versus superposition of two opposite phase pulses traveling in the opposite direction. So when they superimpose at the symmetry point, okay, half the string on one side is going to have the same sequence of shapes that the reflection of a single pulse from a rigid boundary is going to create the shapes of. Because the constraint is the same. Basically, the pulses as they overlap, the symmetry point in the string, which I've shown with a dotted line on the diagrams on the right hand side, the point on the string at that symmetry axis will have zero displacement because the two pulses opposite phase displacements always cancel each other. And that is a constraint faced by a rigid boundary point, that is displacement has to be zero because it's a hard boundary, it's rigidly attached at that point. So that is why they have that same kind of behavior on when you compare that aspect of the two systems. Okay, now we come to the second part of reflection of pulses. That is, if there's reflection at a what we call a soft boundary or a flexible boundary. So reflection of a transverse pulse at a soft, basically a flexible boundary instead of a rigid boundary. Now imagine a long string which instead of rigidly being attached to a wall. Rather, it is attached to a ring which can slip without friction, or which can slip freely up and down in the transverse direction on a smooth fixed pole. This is a ring which can slip on the pole freely. Excuse me. So this time, the end of the string which is attached to that side, the ring, it it's basically forms a flexible boundary, because that point can move without any resistance, any mechanical resistance offered by the medium. It can move freely without any such resistance or any such force. So we have a transverse pulse traveling in this direction. Okay, so this time what will happen is that as the pulse comes to that point P, because the point P is attached to a ring which can slip freely on a pole, this is what will happen. Okay, so the reflected pulse is in phase. That is, there is no phase inversion with respect to the incident pulse. And also, you'll see that as the pulse is progressing in this sense, kinetic energy is decreasing and potential energy is increasing. So the string is getting more and more stretched, because the points on the string are having more and more transverse displacement. Momentarily, all the particles reach the maximum displacement. So the kinetic energy tends to zero because all particles have reached their respective maximum transverse displacement. Particle velocity becomes zero. And then again, potential energy is converting to kinetic energy. So whatever energy it started with as a combination of certain kinetic energy plus potential energy, here it is converted to that maximum potential energy. But now again, it is converted to a combination of kinetic plus potential. Now this can also be understood as what is happening on half the side of a string which is having two pulses overlapping, but such that the pulses are in phase, or they are having no phase inversion with respect to each other and traveling in opposite directions. So if two such pulses overlap, then at the symmetry point, you will see that there will be a net transverse displacement, which is the sum of the heights of the two pulses for a moment. And then the pulses will cross each other. So what is happening to half space in that situation is what is happening in this case of reflection at a flexible boundary or a soft boundary. Yeah, right. I will. This is the heading part. So you can try and visualize this yourself, that if you have a situation where you have two pulses like this. So what happens as they overlap? And by the time they overlap completely, this kind of thing will happen. Then as they cross each other, so this kind of sequence of snapshot pictures you can see is such that what is happening on either side of the string, in this case the left hand side of the symmetry point of such a superposition, will match what is happening in the case of the reflection. Okay, so this is not only a very interesting but a very important aspect to understand. Okay. So end of the day, the thing that we should keep in mind is that for a transverse mechanical pulse reflecting from a boundary, if the pulse is reflecting from a rigid boundary, then it inverts in phase and reflects. And if it's reflecting from a flexible boundary, then it reflects back in the same phase. Okay. Now let's see how this becomes important in application questions. So these are like more specifically JEE Advanced type of questions. Not really expected at JEE Mains level, but definitely expected at JEE Advanced level. So let's look at an example question like this. Now in this, what we have is we have a combination of two strings or two threads, you can say, which we have tied together in a knot at a particular point. So this is a comparatively lighter thread, and then we have comparatively heavier thread, which is tied together like this. So this is a thread which has linear mass density mu2, let's say, of 0.9 grams per centimeter. And this is a comparatively lighter one which has linear mass density of 0.4 grams per centimeter. Now what is happening is that there is a harmonic wave coming from some source traveling along this. So a harmonic transverse wave of frequency 10 hertz traveling at a speed of, let's say, 25 meters per second is incident on the junction coming in from the side of string 1 as shown. String 1, this is our string 2 like this. So find frequency wavelength k omega and v, that is propagation speed of the wave transmitted onto the string 2 from the junction, and B, the wave reflected back into string 1 from the junction point. And secondly, if the incident wave shown has an amplitude of 2.4 millimeters, then find the amplitudes of the reflected and the transmitted waves. So this is a very technical type of question where our understanding of wave equation and our understanding of reflection and transmission at a boundary point is important. Okay. So the hint I will give you is that reflection from a rigid boundary causes phase inversion, but rigid reflection from a flexible boundary does not cause phase inversion. And transmission will always be in the same phase. Okay? Because what is happening is that the incident wave coming in and hitting the junction is causing the junction point to bounce up and down in simple harmonic motion. So that junction point is acting like the source for the transmitted wave. So that junction point acting like a source will create a transmitted wave which is in phase at that point where the transmitted wave is generated with respect to the junction point. So the transmitted wave will be in phase as the incident wave. But the reflected wave, whether it is in phase or in opposite phase, that depends on the nature of the boundary, whether it is flexible or rigid. So here you will see that it's not exactly like a fixed boundary, but at the same time, the string on the other side of the junction is heavier in gauge. It has a larger linear mass density. So in doing a question like this, we'll always assume that if the incident wave is on the lighter string and the reflection is happening from a junction where on the other side the string is heavier, then we have to treat the junction point like a rigid boundary. For reflection, we have to treat the junction point like a rigid boundary. So now just try to understand what all you need to do to solve this question with this information. Okay, so hopefully you've thought about the approach to the question. Now I will go through the working myself for you. Okay, so the first thing we want to do here is we want to represent each of the waves with a proper equation. The incident wave, the reflected wave, and the transmitted wave. We want to represent all three of these with proper equations. And in those equations only we will find how to populate each of the parameters, that how much the amplitude of this one is, how much the amplitude of that one is. So how to find the relationship between those using all the concepts. So what we can do is we can take a junction point as the point x equal to 0 and take this as a positive x direction. This will be the most convenient way of representing the coordinate frame. Okay. So then what happens is our incident wave let's say we write the incident wave as y incident is equal to some incident amplitude into sine omega t minus k1x, let's say just. Okay. So again, just to simplify matters, let's say we have taken the phase constant phi as 0 for the incident wave. So it's traveling in this direction. So it's traveling at a speed v1. So here k1 is equal to omega by v1. Omega is 2 pi f, where f is the frequency of the source of the incident wave. And v1 is equal to square root of t by mu1, which is given to us as, these things are all given. So I think v1 was what, 25 meters per second or whatever. Yeah, 25, and mu1 is 0.4 grams per centimeter and all that. So frequency is 10 hertz. Mu1 was. So now what will happen is that this will cause the junction point to oscillate up and down like this. So that will create a transmitted wave that is going down this thing. So this is a transmitted wave. It will also cause a reflected wave to come back at the same speed v1 because it's propagating in the same string. So our transmitted wave will have an equation, let's say yt, that is some transmitted amplitude into sine omega t minus k2x. Okay, so k2 here is equal to omega by v2, where v2 is equal to square root t by mu2. So v2 is equal to square root of mu1 by mu2 times v1. So this tells me that v2 will be equal to 2/3 of v1, 50 by 3 meters per second. So this is the speed of the transmitted wave. Okay, and this also tells me that k1 is equal to 2 pi by lambda 1, where lambda 1 is v1 by f, 25 by 10, or 2.5 meters, and k2 is 2 pi by lambda 2, where lambda 2 is v2 by f. So it is 5 by 3 or 1.67 meters. So this and this become the wavelength and the velocity of the transmitted wave. And one important thing here is that the transmitted wave is in phase at x equal to 0, that is the junction point, with the incident wave. So you can see that y incident at x equal to 0, the junction point is sine omega t, okay, and y transmitted at the junction point is some transmitted amplitude but into sine omega t. So they are in phase at the junction. That's why there's no phase term additionally over there. Okay. Just write down up to here. So now in this, one more thing we know is the amplitude of the incident wave. That is also given to us. It was whatever 2.4 millimeters. So now we need to calculate amplitude of the transmitted wave. And we also need to write the equation of the reflected wave, which we haven't done so far. Okay, so now the reflected wave, let's write the equation for that. So this is where we have to understand two things about the reflected wave. One, that its direction is of propagation is along the negative x-axis. So it propagates along the negative x-axis. And secondly, it has phase inversion with respect to the incident wave at the junction, because the junction will act like a rigid boundary. And the reason for that is simple, that mu2 is greater than mu1. The string on the other side of the boundary is having more density or more inertia. Hence, it will act like a rigid boundary instead of a flexible boundary. Okay. So accordingly, we'll write the equation of the reflected wave as some amplitude which you don't know into sine omega t plus kx, because it's traveling in the opposite direction. This k will be k1 because it's traveling at the speed b1 equal to square root t by mu1, which is 25 meters per second. Okay. This and some phase constant, which we now have to find out. This we have to find out. So what is happening now is that you see that at x equal to 0, that is a junction point, what is the effect of the reflected wave? It is AR sine omega t plus phi, and the incident wave was A incident sine omega t. Now this must be phase inverted. So that shows us that phi should be pi. So therefore, our reflected wave should have an equation like this. Plus pi. And this should have all these properties. Okay. Now the only thing remaining is to calculate the two amplitudes, for which we'll use two important concepts. We have two unknowns. Okay. The reflected amplitude AR and the transmitted amplitude AT. So for that we have to use two additional equations based on two additional concepts. One is that there is total conservation of power. So the power transmitted through the incident wave is equal to the power transmitted through the reflected wave plus the transmitted wave. So the power of the incident wave should be equal to the power of the transmitted wave plus the power of the reflected wave. That's one concept. And one more concept will come from something more interesting. We'll discuss about that. Just note down up to here first. Okay, so now let's understand the other two equations that I was telling you. So there is power of the incident wave should be equal to the sum of the power of the transmitted wave plus the power of the reflected wave. So half mu1 or we can write this as so this equation becomes like this. So we have so we need a second equation because we have two unknowns. So the second equation is also very interesting, that at any point on string 1, that is where x is less than 0, the net displacement is the sum of the incident plus the reflected. And at any point on string 2, the net displacement is the transmitted wave. Now, since the string are intact, at the junction. Therefore, y net at x minus delta x must be equal to plus delta x. For the limit that delta x tends to 0, that is the displacement, the net displacement at left hand limit of the junction should be equal to the net displacement at right hand limit. Okay. So from that you will see that we have this equation that actually this will become plus and this will become minus. So you're taking x equal to minus delta x. Anyhow, the limit is delta x tending to 0, so it doesn't really matter. So this equation now tells us that A incident sine omega t plus A reflected sine omega t plus pi is equal to A transmitted sine omega t. When you put the limits, so this gives us that A incident minus A reflected is equal to A transmitted, or A incident is equal to A reflected plus A transmitted. So the amplitude of the reflected wave plus the transmitted wave must be equal to 2.4 millimeters. This is our second equation and the equation we had written above. Solving these two equations, now we can get the the reflected and the transmitted waves amplitudes. Okay, so this is a bit of a complicated part of superposition of waves. Okay. But this is the reason why you need to understand reflection of, I mean, this is part of the reason, apart from simple questions which are directly based on reflection of pulses. So you need to understand the difference between rigid boundary and flexible boundary. Okay. And also the entire thing of how to write wave equations, how to adjust the quantities in the wave equations, which of them depend on the medium, which of them depend on the source, and things like that. All right, so with this, we complete today's session. Next session, we will discuss about standing waves on a string, which has two boundaries at either end. Okay. So, for example, a string between two rigid supports, that becomes a system which has, two hard boundaries. And there are harmonic modes for standing waves which are created between the two boundaries. Whereas a string can also have a flexible boundary at one end and a rigid boundary at the other end, or vice versa, or both flexible boundaries also for that matter. So they will have different standing wave patterns. So we'll discuss that in the next lecture, and with that we will finish transverse waves, the first part of wave mechanics, moving on to sound after that. And the early part of sound will be almost like a repetition of the same concepts, but being applied to longitudinal waves rather than transverse waves. So anyhow, that's it for today's session, people. Wish you all the best. Have a nice day.